Last week we saw that a preferred way for computing the QR factorization was to use householder transformations because the resulting matrix Q had columns that were better mutually orthogonal when you're finished, when there is round-off error in the computation. So let's have a look and see how we can use that to compute our final result. Well, here it goes. When we use householder transformations, we really compute a unitary matrix Q. We never explicitly compute it, but we compute a whole bunch of householder transformations such that when you multiply them together, you get the matrix Q. And then the R that comes out really is an upper triangular matrix R with zeros below it. And then we use the space below the diagonal to actually store the householder transformations. That's what we did. Okay, so the important thing here is we start with a matrix A and we apply a bunch of householder transforms to it. And the resulting matrix is R top with zeros below it, if we partition like that. And then if you think about it carefully, we saw that this here is actually Q Hermitian transpose. And then you could bring that to the other side to actually see how Q fits into the picture. Now let's go back to this right here. What we know is that multiplying by a unitary matrix doesn't change length. Okay? So this is equal to the minimum over all x of Q Hermitian times b minus a x into norm. And probably we should square this. I suspect that that's going to come in handy. Okay? And that then is equal to the minimum over all x of Q Hermitian times b minus Q Hermitian times a times x. Okay? Now, this right here is the matrix R top with zeros below it. What if we call this vector here y, and we partition that vector into a y top and a y bottom? Okay? Then what you get is that this is equal to the minimum over all x of y top minus r top times x above y bottom. And just like before, we then see that that's equal to the minimum over all x of y top minus rt x squared plus the 2 norm of y bottom squared. Okay? And then this can be exactly solved, and the x that solves this gives you the optimal solution. Okay? Because this we can't do anything about. But this we can make equal to 0 by solving r top x hat is equal to y top, and that x hat then is the optimal solution. Now what does that mean? What that means is that we should take our matrix B and we should apply Q Hermitian transpose to it from the left. And then we should take the top part of the vector that comes out of that and use it to solve this upper triangular system. But what does that mean? Well, this here is Q Hermitian. So what it means is that we want to take our vector, where can we do this? We want to take our vector B, and we want to apply one by one the householder transformations to it to compute our vector Y. So the procedure now becomes, take your right hand side, take the householder transforms that you stored below the triangle and apply them to B one at a time. That gives you a new vector Y, which you then want to partition into a top part and a bottom part. The bottom part you discard, you take the top part, and you use it to solve for the optimal solution. Here's another way of looking at it, now that we've had this insight. If you start by considering AX approximately equal to B, the way you can sort of see how this works is, oh, what I can do is I can apply the householder transformations on both sides, and this approximately equal continues to exist, and notice that the lengths of the vectors on both sides stay the same. Okay? And then once you're done with that, this here is our matrix R top with zeros below it, times X is approximately equal to this updated vector, which is now Y. And then you solve, you cut your Y in half, you solve with the top part, and you get your optimal solution. And that's a convenient way of remembering how the process fits in with how the householder transforms are used to make the matrix into an upper triangular